Hi, everybody. We're going to talk a little bit more about covalent bonding today, and we're going to look especially at the connection within a covalent bond. So, looking at ionic bonds, it's a little bit easier to predict the connection because all we're communicating in an ionic bond is the lowest ratio of ions within the lattice. But with covalent molecules, it's a little bit harder. Sometimes covalent molecules exist in a lattice, like we saw yesterday with the atomic solids, right? But sometimes covalent molecules exist as discrete molecules. So this term discrete in chemistry means something a little bit different than it means in society. So when we're talking about a discrete molecule in chemistry, what we're talking about is a group of atoms that are connected to each other, but not connected to a larger lattice. They stand alone, they're individual. So it's an individual molecule not connected within a lattice. Like, for example, water looks like this or something like this, right? And water can be connected to a larger crystal to make ice, but more often, water exists as individual water molecules that are flowing past one another in liquid water, or are even very, very far apart, very far away from the next nearest molecule when water is in the gas form. And so this makes covalent molecules a little bit harder to predict the connections, how all the atoms are connected within the covalent molecule, because they're not just organized based off of positives next to negatives, right? So we need a system in predicting how things are attached to each other. So welcome to Lewis dot diagrams for molecules. That's exactly what the Lewis dot diagram model helps us to see. How are atoms connected within a covalent molecule? Now, we've talked about Lewis dot diagrams before for atoms, so we're going to build off of that knowledge and take it a step further and talk about molecules. Some of these are very easy to see the connections. Let me show you one of those. For example, when we're looking at hydrogen connecting to another hydrogen, we can draw the Lewis dot diagrams for each of the hydrogens. And if we look at the electron configuration, right, the electron configuration for hydrogen has one electron in it, 1s1. And so what we see here when we look at each of these individual molecules is their octet is not complete. And we know that the completion of an octet is what drives a covalent molecule. The completion of an octet is what drives the formation of a covalent molecule. So in the case of hydrogen, it's fairly easy to see what the connections are going to be, right? Each one needs one more electron. Let me draw this one in a different color. Each one needs one more electron. They can share with each other. And so the two electrons are going to be shared in both directions. So we get a hydrogen connected to a hydrogen. They both share it, and now each one has a completed octet. In the case of hydrogen, it's a duet, right? and therefore it forms a stable covalent molecule. So it's kind of easy to see the connection when it happens in something very simple, like your hydrogen molecule. However, when we start to get things that are a little bit more complicated, like CH3COOH, for example, it gets a little bit more difficult to predict the connections within the molecule. And so we need a system to help us correctly predict these connections, which is the Lewis dot system. So I'm going to introduce you to this system, and then you're going to go practice this system a little bit with some of these molecules. All right, so let's start walking through this system with water as an example. All right, in the Lewis dot system, to help us predict connections within a covalent molecule, we're going to follow the same steps. Step number 1, you're going to tally up all the electrons, all the valence electrons for this whole molecule. Okay, so for water, we have 2 hydrogens. So hydrogen plus hydrogen, and then we have 1 oxygen. So each hydrogen has 1 valence electron. Oxygen is going to have 6 valence electrons. So I'm going to get a total number of 8 valence electrons. Remember, in a covalent molecule, electrons are going to be shared because they don't have a big enough difference in electronegativity to actually take the electrons from each other. So all of these 8 valence electrons are kind of communal electrons. You can put them anywhere on the molecule. Just because it came from hydrogen doesn't mean it has to stay with hydrogen, right? It now belongs to the whole molecule. You can put these electrons anywhere in order to satisfy the octet for everything in this molecule. All right, step 2, we're going to connect everything together with single bonds. Now, there is a complication here because we have to figure out what molecule is going to go in the middle, and this is called a central atom. And this can be the trickiest part to writing a Lewis dot diagram, is choosing the central atom. So here's a couple hints to help you choose the central atom. First of all, the central atom can never be hydrogen or helium. Remember, hydrogen and helium only have 1 energy level. The most they can hold is 2. So if you connect hydrogen to anything else, it already has 2 electrons. You can't connect hydrogen to a second thing. It can't be your central atom because hydrogen can never connect to more than one thing. Same with helium. So you're never going to make hydrogen or helium your central atom. The other hint I have for you is it's usually the least electronegative thing, which is listed first. In a compound, you may have noticed that they usually list atoms based on electronegativity, and they are listed from least electronegative to most electronegative. So this actually isn't true for water. It's one of the only examples it isn't true, only because hydrogen is listed first. But usually that central atom is listed first. Why are the least electronegative things central? Well, because if it's not very electronegative, that means it's not going to work very hard to steal electrons from something else. In other words, it's more willing to share. So the thing that's in the middle that shares with multiple atoms, you want that to be a very good sharer. So the least electronegative thing is usually the central atom. Okay, so in the case of water, our first rule rules out hydrogen, so our central atom must be oxygen. So we're going to put oxygen in the middle, and we're going to connect everything else to it with a single bond. Now, a single bond You have to know a little bit about a single bond. A single bond is actually made up of 2 electrons. Now notice I drew them as a line. You can also draw them as a dot, as 2 dots that are connected. Eventually we write so many dots, we get sick and tired of writing dots. So instead of writing 2 dots, we draw it as a line. So you can draw it either way. You can use dots, you can use lines, as long as you remember that a single bond, which is written as a line, is going to contain 2 electrons. So I've drawn 2 single bonds here, and therefore I have used how many electrons? 1, 2, 3, 4. I've used 4 electrons. So I'm going to keep track of electrons here. I started with 8. I just used 4. Now I have 4 electrons left. Okay, so now I get to step number 3. I'm going to distribute remaining electrons in pairs around things that still need an octet. So let's evaluate who still needs an octet. When you're counting electrons, the things that you're going to count electrons that are on that element by itself, as well as electrons that it's sharing. So if we look at hydrogen, hydrogen is sharing 2 electrons. Hydrogen only needs 2 electrons, so hydrogen has a completed duet. Same thing with this hydrogen. It's completed. Now look at oxygen. Oxygen has 1, 2, 3, 4 electrons with it. Now hydrogen needs 8. Hydrogen needs an octet, so oxygen doesn't have enough. So oxygen needs more electrons. We're going to take these 4 remaining electrons and put them around oxygen. Before we do that, I just want you to notice that the bonding electrons, the electrons that are in between hydrogen and oxygen, notice they're counting for both hydrogen and oxygen. They are being shared, right? Okay, so we're going to take these remaining 4 electrons, put them around oxygen. 1, 2, 3, 4. Notice I put them around oxygen in pairs. You always want to keep electrons in pairs. You never want to put electrons on as single electrons. Once you get higher into chemistry, you may learn how to break that rule, but for now, we're never going to deal with single electrons. All right, so I put 4 around. I've used 4. I now have 0 electrons left. Let's evaluate who has an octet. So in this case, we're going to find ourselves in 3 different possibilities. So I'm going to put my number 4 over here. We're going to have 3 different possibilities. Possibility A is going to be everyone has an octet. Octets check. That means, and you are out of electrons, which means you are done. Okay, so let's check. Does everyone have an octet? Hydrogen has 2, hydrogen has 2, oxygen has 8. Yeah, everyone has an octet. Are we out of electrons? Yep. We had 8. We used 4 for the bonds. We used 4 as lone pairs. That's what those electrons are called that are on oxygen but not shared with hydrogen. They are called lone pairs. Okay, so we used 4 in our bonds. We used 4 as lone pairs. We now have 0 electrons. Yes, we're out of electrons, which means we're done. This is our Lewis dot diagram for water. Let me redraw it again without all the marks around it so you can see exactly what it looks like. There you go. There is our Lewis dot diagram for water. Okay, so that's our first possibility. Everyone has octets. We're out of electrons. We are done. And that's the case for water. All right, let me run you through the next 2 situations, and we will see those another day. Okay, so B, the situation in B is that you're out of electrons, but not all have octets. If you get here, if you run out of electrons, but not everybody has an octet, you're going to try multiple bonds. I will show you one of these, but the catch with this one is you can't try multiple bonds before you hit step 4. If you try multiple bonds in step 2 or 3, you might be able to set up something that looks right, but it will be wrong. So you can't try multiple bonds until you run out of electrons and realize not everyone has an octet. All right, the third scenario you might see is that all have an octet, but you still have electrons. Again, this is a special scenario. It's one of our exceptions. There is a time and place for elements to hold more than octet. We call it an expanded octet. Again, you can't try this until you hit number 4. You go through all the steps, use all the electrons you possibly can, and then realize you have electrons left. Otherwise, you're going to screw up your pattern, right? Screw up your structure. So again, I will show you one of these examples in a later video. But just know for now that option exists. Okay, let me clear this screen and we'll do an example where everything has of 4B. We'll do one of those examples. And then you're going to go try a couple of these on your own. All right, let me give you the example of CO2. So we're going to run through all the steps with CO2. This would be a really good time to pause the video, see how far you can get on this Lewis dot diagram before you get stuck. So pause here. All right, step 1, I'm going to total up all of my valence electrons. So carbon plus oxygen plus oxygen. Carbon has 4, oxygen has 6. I'm going to have a total of 16 valence electrons to work with. Step 2, I'm going to connect everything to a central atom. So I don't have any hydrogens or heliums to worry about, so I'm going to choose carbon as my central atom because it's listed first. It's also the least electronegative between the two. So carbon, oxygen, oxygen. I just connected everything I have with a central bond. You don't have to make it symmetrical, but as you go on, the more symmetrical something is, the easier it's probably going to make your life. So make it as symmetrical as you can. All right, I just used 2 single bonds, so I'm going to subtract 4. I have 12 left. Now I'm going to distribute those remaining 12 around things that still need octets. So everything still needs octets. Oxygen has 2 around it right now. Carbon has 4 around it right now. So let's distribute electrons that we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I just distributed all of my 12. I am out of electrons. So now we check. We're on number 4. Does everyone have an octet? Oxygen has 6, not 8. So oxygen does not have an octet. Carbon has 8. Carbon has an octet. Oxygen has 6. So carbon's the only one with an octet. Oxygen still needs electrons. So here's the question. We don't have electrons. We can't just invent electrons and put them on next to the oxygens, right? We have to use the electrons we have. So this is where you're going to try multiple bonds. So we talked about what a single bond is. A single bond is one line, which is 2 electrons. A double bond, we're going to draw as 2 lines, and that contains 4 electrons. You can also use a triple bond. That's going to be 3 lines, which is 6 electrons. So we're going to shuffle electrons around. For example, notice these electrons that are on carbon right now, they belong only to carbon. So can we move them into a place where they still belong to carbon, but they also belong to oxygen? Yes, we can do that. So we're going to take it off carbon and move it into a place where they still belong to carbon, but now they also belong to oxygen, which is right here. Notice they still belong to oxygen, or carbon. Carbon still has an octet, but now they also belong to oxygen. This oxygen also has an octet, and that's what we call a double bond. Let's do the same thing for the other oxygen. We're going to move electrons off of carbon into a spot where they still belong to carbon, but they also belong to oxygen. And now this oxygen also has an octet. We're out of electrons. Everyone has an octet. This is our structure. Let me draw it again so you can see what it looks like with all the shenanigans around it. There you go. So notice carbon has an octet because it has 2 double bonds around it. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. Oxygen has an octet because it has a double bond with carbon. That's 4 electrons. And then it also has 2 lone pairs, which is another 4 electrons. So 8 electrons around that. And this is the Lewis dot diagram for carbon dioxide. Notice this one's a little bit trickier, but following the rules helps us to predict the connections inside this covalent molecule and where all of the electrons exist. And this helps us with a lot of different bonding theories that are going to come up as you learn more about chemistry, like the Vesper theory, which talks about how molecules are shaped, and there's a couple other theories, like hybridized bonds, which talk about, again, a little bit of shape, a little bit of how electrons are related to each other, where electrons actually exist inside of energy levels. It helps us in the future when we talk about bonding and anti-bonding orbitals. So this is kind of the foundation for a lot of different bonding theories that are going to come, that we're going to kind of build off of this. So let's practice this. Let's build this really solid foundation so that as we move forward in chemistry and learn a little bit more about bonding, we can build on this foundation. Okay, we're going to practice this. But as it stands, let me know what questions you have, and I will see you in class.